Surviving in space means getting comfortable with the idea of breathing your own waste. On the International Space Station, every breath the crew takes is a recycled ghost of a liquid they would normally flush down a toilet. We built a machine that defies the basic logic of biology, one that converts yesterday's coffee into tomorrow's atmosphere. It is a closed-loop survival strategy that is as unsettling as it is brilliant, and it is not just about keeping 7 people alive in low Earth orbit. It is the blueprint for how we become a species that lives on more than one planet. This is the story of the machine that breathes. Space is a vacuum that wants to kill you, and it does not do it with a bang. It does it with a slow, suffocating silence. Inside a normal house, you survive because the atmosphere is an open system. You breathe in oxygen, you breathe out carbon dioxide, and the trees outside handle the exchange. On the ISS, cracking a window would boil your blood in seconds from the pressure drop alone. So we had to bring the trees with us, except our version comes in the form of refrigerator-sized racks packed with titanium and chemistry. We call this the Environmental Control and Life Support System, or ECLSS for short. For a long time, the plan was to just bring enough oxygen along for the ride. The early days of spaceflight were basically humans sitting on top of giant tanks of air. But tanks are heavy, and in rocketry, weight is the enemy. To stay in space for years instead of days, we had to stop being consumers and start being recyclers. The fix starts with a piece of high school chemistry, specifically the water molecule. H2O, 2 parts hydrogen, 1 part oxygen, held together by a relatively strong atomic bond. If you want the oxygen back, you have to break that bond, and we do that through a process called electrolysis. Electricity from the station's massive solar panels runs through a cell stack filled with water, and the current forces the molecules apart. Oxygen bubbles off one side, hydrogen bubbles off the other, and we pump the oxygen straight into the cabin so the crew can breathe again. The hardware that handles this job is the Oxygen Generation Assembly, or OGA, and it has been the primary source of air for the American side of the station since 2008. But here is where a mass balance problem shows up. If you keep splitting water to make air, you eventually run out of water. And the crew is still exhaling carbon dioxide, a toxic waste product that has to be scrubbed out of the air using molecular sieves, which are basically high-tech sponges that soak up CO2. In the early years of the station, we just vented that CO2 into space. We also vented the hydrogen from the electrolysis. We were throwing away the very ingredients we needed to keep the whole cycle going. Nature does not tolerate waste, and neither does NASA's budget. To actually live in the void, we needed a way to take that waste CO2 and that waste hydrogen and turn them back into something useful. This is where things get genuinely clever. The solution comes from a piece of 19th century chemistry that won a Nobel Prize in 1912, named after the French chemist Paul Sabatier. He discovered that if you take carbon dioxide and hydrogen and run them over a nickel catalyst at high temperatures, they react. The equation looks like this. CO2 plus 4 parts H2 gives you methane and water, CH4 plus 2H2O. Think about what that means for the station. The Sabatier reactor takes the 2 things we were discarding, the astronaut's breath and the leftover hydrogen from the oxygen machine, and it hands back water. That water feeds right back into the electrolysis machine to make more oxygen. It is a chemical carousel. When the Sabatier reactor first launched in 2010 on the Space Shuttle Discovery, it felt like we had cracked the puzzle of long-term survival. But the loop is not perfectly closed, because thermodynamics does not do favors. The Sabatier reaction only recovers about 54% of the oxygen from the CO2. The rest gets trapped in the methane, CH4. And here is a bit of a secret. We do not keep the methane. It is a highly flammable gas, and storing it on a space station is a terrible idea for reasons that involve common sense. So we vent it. Every few hours, the ISS literally releases a cloud of methane into the vacuum. It is a visible sign of the inefficiency we are still trying to eliminate. Here is the full cycle in human terms. An astronaut wakes up and drinks a cup of coffee. That coffee was made from water that, 24 hours earlier, was another astronaut's urine. The body processes it, and the astronaut exhales CO2. The life support system scrubs that CO2 from the air, mixes it with hydrogen, runs it through the Sabatier reactor, and produces water. That water is then electrolyzed to create the oxygen being breathed right now. Today's coffee is literally tomorrow's air. It sounds unpleasant, but it is the most pristine water anyone has ever tasted. The water recovery system on the station now reclaims about 98% of all liquid waste, including sweat and humidity from the air. The station has become something close to a self-sustaining biological island.
If you are the kind of person who finds closed-loop chemistry and space interesting, you are exactly who this channel is for. Hit subscribe so you do not miss the next one.
But machines in space break, and they break often in ways that are hard to fix. The original Sabatier reactor degraded so badly that it was removed in 2017. Catalysts get poisoned, pumps fail, and the harsh environment of space grinds everything down. When the machine that breathes stops working, the station becomes a very dangerous place very quickly. You might assume you would notice if the oxygen levels dropped, but you would not. Carbon dioxide is the real killer. In zero gravity, convection does not work. On Earth, your warm breath rises away from your face, but in space, it just stays there. If the station's fans stop moving the air, a CO2 bubble can form around an astronaut's head while they sleep. They would suffocate in their own breath without ever waking up. That is why the station is never silent. It is a constant 70-decibel hum of fans and pumps, the sound of life being forced into a place where it does not belong. If that sound ever stops, you have a serious problem. When the main machines fail, the backup system is something called SFOG, which stands for Solid Fuel Oxygen Generation. These are canisters of sodium chlorate and iron powder that release oxygen through a chemical reaction when ignited. They are the ultimate fallback, but they are dangerous on their own. In 1997, on the Russian Mir station, one of these candles caught fire and turned into a blowtorch that melted through hardware and blocked the path to the escape craft. The crew survived, but it was a stark reminder that even the backups can kill you. Right now, we are testing a new generation of these machines, the Advanced OGA. The goal is to push that 54% recovery rate all the way to 100%. One candidate is called the Bosch reaction, which would produce pure carbon instead of methane. But the Bosch reaction is messy. It generates solid graphite that clogs the machinery. And imagine trying to run a space station while constantly scraping soot out of your life support system. It is a trade-off that engineers are still working through. We usually talk about the ISS as a laboratory or a docking port, but that misses the point. It is more accurate to call it a biological extension of the human body, a fragile metallic lung exhaling the future into the void. Every time we improve the Sabatier reactor's efficiency by a fraction of a percent, we are extending the leash that ties us to Earth. We are learning how to live in a world where nothing is wasted because there is nothing to waste. On Earth, we have the luxury of thinking our resources are infinite, but in space, that illusion disappears instantly. Once we figure out how to perfectly close the loop, the journey to Mars stops being a dream and becomes an engineering schedule. We will no longer be visitors in the dark. We will be part of the ecosystem we brought with us. It is a strange thought that the future of humanity depends on a machine that turns urine into air. But space has a way of making the most unpleasant things look like the most beautiful engineering we have ever pulled off. And if we can get the Bosch reaction to work, we might just be able to 3D print spare parts out of the carbon we breathe out. That story is coming soon.